Last week, we talked about magnetic fields and introduced the concept of force on a charge moving in an electric field. I'm sorry, magnetic field. And we're going to add just a few other pieces to that. I'm going to reinforce some of the ideas from last week and discuss some of the questions that were brought up during the quiz. Then we're going to add kind of the change in flux and how that induces current and go into inductors, so we can go into inductors and circuits, which might sound like a lot, but when you see it all kind of pulled together, what you're going to see is our inductor resistor currents, circuits, have very similar behavior to our capacitors and circuits. So it's not too terribly much to add in there. One of the things I wanted to talk about first, though, was this idea of a charge moving in a magnetic field and the force that it exerts. And then so we had some fun with our right hand rules. And remember, what I said with our right hand rule is that I can think of it as the general thing as A cross B. So it can be any quantities that I'm crossing. They're perpendicular to each other. They're normal vectors, that is. We take the sign with the cross product to count for the pieces that we're looking for that are perpendicular. So essentially, if something is perpendicular, then we have sine of 90, and so we get the whole darn thing. If it's not, we're pulling out the piece that will be perpendicular, and that's going to give us our net whatever we're looking for. And what I was telling everybody is that when we're doing our right hand rule, left hand rule too, that our first letter, our A, so when we're looking at our V cross B, would be our velocity. And then our next letter that's being crossed is going to be our middle finger. And then the resultant direction is our thumb. So in other words, if I have X cross Y, well, I'm not going to get an X or a Y, I'm going to get a Z. If I have a Y cross Z, I'm going to get an X. And then I was drawing out the 3D kind of pictures of our axes. So you could kind of start orienting your hand, and then it gets kind of fun because then we start doing all sorts of weird things and contort ourselves. I've walked a few people through the math, but I'm not going to do that here because there are some eyes that looked terrified. So use the right hand. It'll help you just be slow and methodical and kind of write out on paper when you're doing it just in terms of axes. But when we're looking at charges here, see, I'm going V cross B. So I put my hand pointing in the direction of the velocity. And see, and then my middle finger, that's the B, is going to go oish, like that away. So my sine theta, see how fun it is? My sine theta is pulling out the perpendicular component. And that tells me that the net force is going into the page on this. So let's do this again. I'm here. We can kind of, actually that's going to be an easier one. Point the middle finger in the direction of the magnetic field, and my thumb gives me the net direction of the force. And this, just play with it some. Look at the pictures where you know what it comes out to be. Reminder, this is only the positive or current. Conventional current we treat as a positive, and our left hand is for anything negative. So why is there a force? That was one question I didn't get hit with that I was kind of expecting. I did post some videos kind of giving a demonstration on it. And I would think the easier way to think about why there's a force is going back to the first video that I showed you with the levitating coil, right? So we induced current into the coil, and what happened? So I had some stationary magnets on a table where the person doing the demo had stationary magnets on the table, and then hooked up the coiled wire to a current source and then turned the current on. So nothing was happening with the coil between the magnets. It wasn't jumping to one side or the other or jumping up or down. But all of a sudden when they ran current through the coil starts levitating because of the opposing magnetic fields causing that repulsive behavior. So what was happening there? My charge is moving in that line, and all of the sudden I have repulsive magnetic. So a moving charge has an electric field and a magnetic field. It's got to be moving. A magnetic field doesn't induce charge, though, unless it is changing. So a changing magnetic field makes things go, or if I have a moving charge, I also have a magnetic field. So you can think of like my little tiny electron is both moving with an electric field going some direction. Well, perpendicular to that direction is also a magnetic field. Awesome. And that's what's happening when we see the charges moving in the questions that we've been given and kind of the net force. And then we can look at things, and y'all were getting to this question. And I was hearing a lot of, well, there's an equation I've been using that worked. Which is, okay, that's fair. But let's think about why it works. And one of the discussions I was having with folks was just a reminder from 161 when we talked about something turning or moving in a circle. So changing direction, going from other than straight. R is that radius of curvature of the turn. And V is our tangential velocity. So with our V cross B, the first thing that folks were asking is, well, how do I know what the direction of my magnetic field, the sign for the angle between my velocity and my magnetic field? And what I was saying to you is to think about it in terms of, I have my velocity going one way, I have a net force pointing in. So if my net force is pointing towards the center, I can look at this and be like, okay, so there's my force, my resultant. Let's see what's happening. So I am using the right hand. My finger is pointing in the direction of the velocity, and my middle finger is coming up out of the page. So if these two are totally perpendicular, which they are, because remember, if I'm turning, the net force points towards the center of the circle, center of the curvature, then my magnetic field's coming out at me and all my angles are 90. I have everybody's perpendicular to each other. So remember, a force net for something center seeking, force net for center seeking, center, I'm going to abbreviate this, skiing, well, whatever, is mv squared over r. Or how I was writing that, so it doesn't look so kind of ugly, is that if I am going in a circle, there must be a net force, and we gave that this subscript C for a center-seeking force. In this particular case, our center-seeking force is that Q, or the V cross B. And then we looked at kind of this V cross B is the big piece, right? The VB sine theta. Theta is 90, so it's just those two. But this doesn't get interesting unless I actually have a charge. But although I would have to have a charge to have a velocity, otherwise there'd be nothing moving. So that's not very exciting. There. Moving charge in an electric field. I am going to, I'll do this. No, actually, I'm going to stop here. And I'm going to come back to the change in flux and then the direction of the induced field on the next video.